Hello, I'm Seema and welcome to part 4 of the chapter Redox Reactions. In part 3, I told you about oxidation number and I told you how do we determine the oxidation number of an atom which is present in a compound. We will move ahead with our discussion of oxidation numbers in this video. Now we know that atoms of elements can have different oxidation numbers. If you have more atoms of the same element in the same compound, each atom may have a different oxidation number based on what other element is it attached to. So oxidation number is actually only a theoretical charge that we allot, assuming the electronegativity difference between the atoms that are attached by covalent bonds. And we simply assume that instead of electrons being shared between covalent bonds, the more electronegative atom pulls the electron totally towards itself and the electropositive atom loses that electron to it, thereby acquiring a positive charge, and the one that gains the electron acquires a negative charge. So it is only an apparent charge that is there in the covalent compounds. It's not a real charge. Yet, for all practical purposes, for all calculations, we assume it to be a proper charge. So, having understood that, is there a trend when we go in the periodic table? Do we see a trend in oxidation number? Yes, we do. As we move from left to right across the periodic table, if you use the representative elements, we find that the oxidation number increases from +1 to +7. So, the representative elements are the elements, all the elements except the transition elements. They give you the representative elements. So, group 1, group 2, and then come the 10 groups of the transition elements, then group 13, 14, 15, 16, 17. 18 of course does not combine, therefore would always have an oxidation number of 0. They would never have any charge. So we find that this trend is seen that the oxidation number increases as you move across the representative elements, and the maximum oxidation state that an atom can have in a compound, that an atom of one element can have, that maximum value is the one given by this. And how do we calculate this maximum value which any atom of any group will have? You can calculate the maximum value, the maximum oxidation state that the atoms of a group can have by a simple formula. For the first two groups, it is equal to the number of valence electrons of the group. That is for group 1 and group 2. They have 1 electron and 2 electrons in their outermost shell, which they can lose in order to acquire the octet. Therefore, they would have oxidation state of +1 and +2. But when you come to group 13, 14, 15, 16, 17, how do you calculate the maximum oxidation state in these cases? You subtract 10. From 10, you subtract you subtract 10 from the group number. So, 13 minus 10 will be 3. So the maximum oxidation number of the elements of the 13th group will be +3. For the 14th group, the maximum oxidation state will be 14 minus 10, which is +4, 15 minus 10, +5, 16 minus 10, +6, and 17 minus 10, +7. As I told you that there is a possibility of this, if you have more than one atom of the same element present in a compound, their oxidation states would be different. They would vary depending on which other atom of which element is that atom combining to. So every atom, even if it is of the same element, will have a different oxidation number. And therefore, when you are reporting the oxidation number of the atoms of the same element in the compound, we give an average oxidation state of such atoms where you have multiple atoms of the same element. So this, when you can have more than one, when we are giving this value, this is the value of the maximum oxidation state. Beyond this, it cannot have an oxidation number or oxidation state greater than this number. So what is the trend that we observe in the periods? In the periods of representative elements, we find that the oxidation number or oxidation state increases by 1 as we move from left to right. So it goes from +1 to +7, from group 1 to group 17. So metals have a positive oxidation number and non-metals may have a positive or a negative oxidation number. As you know, metals always lose electrons. Therefore, metals always have a positive, and if they lose electrons, they acquire a positive charge. Therefore, they would always have positive oxidation numbers. But non-metals, if they are reacting with metals, they are more electronegative, so they will have negative oxidation numbers. But if a non-metal is reacting with another non-metal which is even more electronegative than it, then it is more electropositive in comparison to that. Therefore, in comparison to that other element, it would acquire a positive oxidation number. So, metals always have positive oxidation numbers because they always lose electrons. But non-metals can have both positive as well as negative oxidation numbers depending on what is the other atom which it is combining with and what is the electronegativity difference with it. Is it more electronegative than that, or is it more electropositive than that? That will determine whether it has a positive charge or it has a negative charge. So, non-metals have positive or negative oxidation numbers, and in the case of transition elements, they have several oxidation numbers. So they have several, but we do not go into the details of these, the oxidation numbers of the transition elements right now. The highest oxidation number for a representative element is equal to the group number for first and second group and group minus 10, group number minus 10 for the other groups. That is 13 minus 10 is 3, 14 minus 10 is plus 4, 15 minus 10 is plus 5, and so on. So what do we see? What is the trend that we see? So oxidation number increases across a period. As we move from left to right in a period, the oxidation number increases. Oxidation number and oxidation state are actually, they mean the same. And these are terms that are used interchangeably. You call them oxidation states or you call them oxidation numbers. There was a German scientist who was called Alfred Stock, and whose name was Alfred Stock. He gave a notation or a way to represent the oxidation states of metals in compounds. And this way of representation of the oxidation state of the metals in compounds is known as the Stock notation. It is a way to represent it. So it is known as the Stock notation. So German chemist Alfred Stock, he gave the Stock notation. In the Stock notation, the oxidation state or the oxidation number of the metal is given. And how is it given? We write it in Roman numerals. And we write the oxidation state in Roman numerals and we put it inside a bracket. A bracket is also called a parenthesis. You must be aware of it. So it is a Roman numeral in parenthesis after the symbol of the metal. Remember, Stock notation is only a notation for metallic atoms. It is not given for non-metals. It is not for negatively charged oxidation states. It is only for metals which only have, and we know metals always have positive oxidation states. So, for example, you have gold, Au having +1 charge, Cl, that is Aurous chloride. Aurous is +1 is the oxidation state of gold. So in AuCl, the +1 state will be represented by 1 in Roman numerals and inside a bracket. So how do you write the formula? Au1Cl. In auric chloride, the charge on gold atom is +3. So you will write AuCl3 is the formula, but you will write the charge in a bracket in Roman numerals after the symbol of gold. Stannous chloride is Sn2Cl2. You can understand here the charge on stannous, that is stannum, is 2. Stannous is tin. So the charge here is 2. And stannic chloride is SnCl4 and the charge on this is +4. So in a bracket, in the Roman numerals, you write +4. So this is how you represent the oxidation states of metals in formulae by Stock notation. Having understood this, let us move forward. Alright, there's another example. Hg2Cl2 is mercurous chloride and the charge here in Hg2Cl2 is 1. And it is the reduced form of Hg2Cl2. And Hg2 is 1. The charge over it is 1 and here the charge on Hg, mercury, is 2. and the formula is HgCl2, and therefore the oxidation state of mercury in HgCl2 is 2, plus 2, which is represented by 2 in parenthesis. Now, I have explained how do we present this, or how do we represent them by stock notation. Now the question is, how do we know what is the charge by just on the metal, just by looking at the formula? Is there a trick? Is there a way that we could find out what is the charge on it? Remember, in the previous video we did the various steps and I gave you the different rules of allotting the oxidation number to an element. So what do? We keep these metals in mind, and looking at the formula and the charge on the negative ion, we determine what will be the oxidation number for the metal. For example, all halogens have a charge of -1. So if you have AuCl, it means the charge on Cl is -1. If it is -1, then the AuCl should be a neutral compound. So what should be the charge on Au? It should be +1. So that tells you that the charge on gold will be +1. In auric chloride, you have AuCl3. There are 3 negative charges because every chlorine has 1 negative charge. So 3 chlorines will have 3 negative charges. So what should be the charge on gold? It should be 3 positive. That is how we determine in auric chloride in the stock notation the charge on gold will be +3, and therefore you will put 3 in a bracket. So that is how, looking at the formula, you can tell what will be the charge on the metal, and then you can write the stock notation. This is the kind of problems that you will be getting in your exams. Let us take another example now, SnCl2. Now tin and chlorine. Chlorine again has -1 charge, and there are 2 chlorines, so there is a -2 charge. If there is a -2 charge, for the compound to be neutral, Sn should be +2. Therefore, in the bracket you see its charge or the oxidation state is +2, right? And in SnCl4, how would you know the charge is 4? Because there are 4 chlorines, 4 negative charges. To balance it, you should have 4 positive charges. Therefore, the charge on tin here should be 4. So that is how you can determine the charges, and that is the kind of problem that you have in your textbook. Using stock notation, represent the following compounds. The formulae of compounds have been given, and you are expected to write the stock notation and write the formula of the compound in stock notation. Now, you have the first compound is HAuCl4. Remember, according to the rules, H always has a charge of +1 and chlorine always has a charge of -1. So how many chlorines are there? There are 4 chlorines, and therefore there are 4 negative charges, and hydrogen has 1 positive charge. So there is 1 positive charge and 4 negative charges, right? So which means that one of the negative charges has been cancelled out already by the positive charge. So gold should have how many positive charges, so that you have 4 positive and 4 negative charges? Hydrogen has 1, there are 4, so 4 minus 1, 3. You need 3 charges on gold. So gold should have a 3 positive charge or a +3 charge. So how will you write the formula in stock notation? It will be HAu, and here you write 3. Remember, we are not writing it for H because H is not a metal, and stock notation is only written for metals. And Cl4 is the stock notation for this compound. FeO, iron, has, you need to find out the charge on iron. Oxygen is -2, so iron should be +2 in order to balance it. So you write Fe and you write 2 in the bracket and O. Fe2O3, there are 3 oxygens. According to the rule, every oxygen has a charge of -2. Oxygen would only have a charge of -1 in the case of peroxides and half in the case of superoxides. You remember that? But this is neither a peroxide nor is it a superoxide. It is ferric oxide. So what would the charge be? There are 3 oxygens, it means and each one has a charge of -2, so 3 2s are 6. And there are 2 irons. Since there are 2 irons and the positive charge should be 6, each iron should have a charge of +3. So you write Fe2, and we use the average. You remember 6? The average of 6 for 2 atoms would be 3. Fe2O3. And the charge on iron is 3. Then we come to copper iodide. Iodine is a halogen. It has a charge of -1. So this should be cuprous iodide. So it should be Cu1. The charge on copper should be 1. Iodine. In cupric oxide, oxygen has charge of -2. So copper should have charge 2 here. So and oxygen is -2. In order to balance that, it should be a +2. Manganese oxide, in manganese oxide MnO, oxygen is -2, so Mn should be 2. And in MnO2, there are 2 oxygens, so -2 into 2, -4. So here in MnO2, the charge on manganese should be +4. So it will be Mn4O2. So this is how you would write the stock notation. Using stock notation, represent the following compounds. So you represented these compounds using the stock notation. So with that, I think you have understood enough about oxidation numbers, and I'd like to explain a little bit more about oxidation number before I wind up this video. Give me a moment. So having understood this about oxidation number, what do we conclude about it? If you take a chemical reaction like 2H2 plus O2 will give you 2H2O. Look at the oxidation numbers of the reactants. Hydrogen has 0, oxidation number 0. In water, hydrogen has oxidation number +1 and oxygen has -2. So oxidation number of hydrogen increased from 0 to +1. It means hydrogen got oxidized and oxygen reduced from 0 to -2. Therefore, oxygen got reduced, right? And anything that helps a substance to get reduced is a reducing agent. So who helped oxygen to get reduced? Hydrogen helped it to get reduced. Oxygen could not have got reduced. What is reduction? Reduction is gaining of electrons. So oxygen could not have gained electrons if hydrogen would not have provided those electrons. So who reduced oxygen? Hydrogen reduced oxygen. At the same time, hydrogen could not have got oxidized if oxygen had not accepted its electrons. So who oxidized hydrogen? Oxygen oxidized it. Therefore, the substance that gets reduced is the oxidizing agent. And the substance itself that gets oxidized is the reducing agent, right? So from these reactions now, you can see whether a reaction is redox or not. How would you know whether a reaction is a redox reaction or not? If the oxidation numbers are changing, then it is a redox reaction. And from the reaction, from our knowledge of oxidation number, we can tell which is the substance that got oxidized, which is the substance that got reduced, what is the oxidizing agent. The substance that got reduced is the oxidizing agent, and what is the reducing agent? The substance that got oxidized is the reducing agent. The oxidizing agent is also called oxidant, and reducing agent is also called the reductant, right? So let us just summarize this. This was the reaction. So what do we understand from this? Oxidation can be defined as an increase in oxidation number. If any atom is undergoing an increase in oxidation number, we say it is getting oxidized. Reduction may be defined as a decrease in oxidation number. So any substance in which the oxidation number is decreasing would be the substance that got reduced. The oxidizing agent would be the substance that got reduced. Therefore, it is also decrease in oxidation number. And it is also known as the oxidizing agent is also known as the oxidant. Reducing agent is any substance that helps the other substance to get reduced. So it itself gets oxidized. So reducing agent should also have the same definition as oxidation. So increase in oxidation number is that for the reducing agent. And it is also known as reductant. And on the basis of this, how do we define redox reactions? The reactions that involve a change in oxidation number would be defined as a redox reaction. On the basis of oxidation number, how would you define a redox reaction? A reaction in which the oxidation number changes would be a redox reaction. Now, on the basis of this, let us do one question. This is example 8.4 in your textbook. Let me explain this. Justify that the reaction 2Cu2O plus Cu2S gives you 6Cu plus SO2. That is the reaction. It is a redox reaction. You have to justify that this is a redox reaction. Identify the species that got oxidized, the species that got reduced, and which species acts as the reductant and which species acts as the oxidant. So let us just write down the equation once more. It is 2Cu2O plus Cu2S will give you 6Cu plus SO2. What will be your job in such a question first? You will have to allot the oxidation numbers for, when we did the stock notation, we learned how to allot the oxidation number for the metal. For the most of the non-metals, you will be knowing the oxidation state. So let us just write down the oxidation numbers first. And then with the change in the oxidation number, we will trace the species that got oxidized, that got reduced, or whether if there was a change in oxidation number, then it is a redox reaction. So we'll solve the rest of the question. Here, oxygen has a charge of -2 and you have 2 coppers. So in order to balance now we are not paying attention to the stoichiometric coefficient, because the stoichiometric coefficient only tells you how many molecules are reacting. You only are concerned about the oxidation states. So we'll say there are 2 copper atoms balancing out 2 negative charges. So each copper should have a charge of +1. That is how there will be 2 positive, 2 negative, sorry, +1. Would be the charge on copper. In copper sulfide, again, sulfur has a charge of -2 and copper has a charge of +1. It is the same situation. Sulfur and oxygen have the same, they belong to the same group and they have the same charge. That is -2. So copper in both these compounds has an oxidation state of +1. And elemental, any atom which is in its elemental state has oxidation state of 0, or its oxidation number is 0. And in sulfur dioxide, now sulfur is more electropositive in comparison to oxygen. So in sulfur dioxide, oxygen has a charge of -2 and there are 2 oxygens. Therefore, what would be the charge on sulfur? It will be +4. So 2 2s are 4, you have 4 negative charges, therefore sulfur should have a +4 charge. So what happened to the oxidation states? Let us see. Copper was +1 here, and copper became 0. So if copper is from +1 state is turning into 0, it means copper oxide here is getting reduced, or we should say copper is getting reduced. Oxygen, take a look, oxygen was -2 here also, and it is -2 here also. Therefore, oxygen is neither getting oxidized nor reduced. It is the copper atom which is getting reduced. And the copper here also was +1 and it got changed into copper 0. That is also getting reduced. So copper in both the compounds is getting reduced from the +1 oxidation state to 0 oxidation state. And oxygen does not change. The oxidation number of oxygen is not changing, so no change is occurring in the case of oxygen. Let us come to sulfur now. Sulfur changes from -2 to +4. So oxidation number is increasing in the case of sulfur. So sulfur is the species which is getting oxidized. So what will we say? We'll say sulfur from copper sulfide is getting oxidized, and copper from both the compounds is getting reduced. Now, what is the oxidizing agent and what is the reducing agent? Anything that itself gets reduced acts as the oxidizing agent. And anything which itself gets oxidized acts as the reducing agent or reductant. Reductant and reducing agent is the same. And oxidant, right? You can call it the same thing. So, what is the oxidizing agent or the oxidant? The substance that got reduced. What got reduced? Copper got reduced, the copper ion. So, copper ion from both the compounds got reduced. Therefore, copper ions present in both the compounds act as the oxidizing agent. And sulfur got oxidized. So, sulfur from copper sulfide is the reducing agent, because it helps to reduce the copper in both the compounds. Itself in the compound which is present in itself, plus the copper which was present in the other compound. The sulfur has helped to to reduce the copper in both the compounds. So this was about oxidation number, and I'll conclude the video here. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.